Okay, so the infiltration and percolation, I think you already heard about this when we talk about the hydrological cycle on our previous meeting. Like here we have like hydrological cycle. Yeah, I already showed you this cycle before. It's the same picture. Here we have, in our focus is now in the soil. Here we have infiltration and percolation with number 6 and 10. Like the number 6 is the infiltration, and number 10 is the percolation. And the water flowing is the same. It's using high gravitational force. Like if it is raining from here, the water is infiltrate to the soil, which is number 6, infiltration. And after the water arrive inside the soil, it becomes the moisture content, number 9. Here is MC, or the moisture, the soil moisture, or the moisture content of the soil. And after that, the water can also going inside again deeper into the soil through the groundwater level. Here is the groundwater level, the line, the blue line, and the water coming into the groundwater level, it is called the percolation, the process called percolation. So we will talk about this thing, infiltration and percolation, number 6 and number 10, and it is closely related to the soil, the ground. First, we will talk about soil moisture. And for this soil moisture, it is mean that the water content in the soil layer, where water can move above the soil surface as capillary water, and can also move downward as gravitational water. So this soil moisture can evaporate from the soil surface, but it is also can going down with the gravitational force to the deeper side of the soil. The water that move above the soil can be evaporated again, while those that move downward will enter the groundwater level and will be called percolation. So part of the water in the soil is evaporated, but part of them is going into the groundwater level. How to calculate this moisture content or the soil moisture? Here we call it with MC, moisture content. Moisture content is the infiltration capacity plus the volume of water seeping from the capillary area. So this two is the water coming into the soil, minus T. T is the percolation capacity. This is the amount of the water going into the soil layer below the groundwater level, and the amount of evapotranspiration in the surface. So the water coming into the soil minus the water coming out to the soil, which is the first one is through the groundwater level, and the second one is through the evaporation or evapotranspiration if the soil is planted. So what is important for the moisture content in hydrology? The first one is the soil ability to absorb surface water, or we name it infiltration capacity. So as you know, if the rain happen, this is the rainfall, and then here we have the soil. Not all of the water is absorbed into the soil. That's why we have like That's why we have like the water running above the soil, because not all of the rainwater is absorbed into the soil. And then here we have the soil ability to absorb surface water, because it depends on the ability of the soil. If it's already reached its maximum capacity, the water, the soil cannot absorb water anymore. So the water from the rainfall will be flowing above the surface of the soil. So it will become the surface water, or we call it runoff water. And the second one is soil ability to store water, soil moisture, and the amount stored. And then after we get the water from the rainfall coming into the soil, some of the water is stored inside the soil, which makes the soil moisturized, which is called soil moisture. And the amount of the water stored inside the soil is also depends on the type of the soil. So if we have like soil which is dry, it will store more water than the soil which is wet, because if the soil is already wet, it cannot store a lot of water anymore. And if the soil is rather dry, it can store more water than the soil which is already wet. And the drainage of water from the surface of the soil to the surface of the groundwater, and vice versa. Here we have the movement of soil moisture. So the moisture content here can go up as evaporation. It also can go inside the soil, inside the water, the groundwater level, as percolation. So here we have two possibilities. It depends on if the evaporation it depends on the sun, but if the percolation, it depends on the groundwater level. And for the infiltration process, previously we talked about the soil moisture. This is the infiltration process, which is when the water enters or absorbs by the soil. The process is called infiltration, and the magnitude of this absorption capacity is different in terms of soil condition. As I said earlier, it depends on the type of the soil also. Some of the soil already wet in the beginning, like because of its type, and some of the soil is dry. For example, the soil which is in the desert area, it's rather dry. Then the soil in the agriculture area, it's rather wet. So the absorption capacity will be different for each type of the soils. And each soil surface has an infiltration capacity, which is called FP here. This is the maximum ability of the soil to absorb rainwater. Here we have rainwater as I that falls on it. So the infiltration capacity, the FP, if it's already full, so it means the soil cannot absorb any rainwater. But if the infiltration capacity is not maximum yet, the soil still can absorb rainwater. Here we have the comparison between the rainwater and infiltration capacity. So if the rainwater is less than the infiltration capacity, it means the water which is coming from the rain is less than the infiltration capacity of the soil surface. It is meant that all the rain will soak into the ground. So all the rain can be absorbed into the soil because the capacity is bigger than the rainfall, which means there's no runoff occur. So there will be no surface runoff in the soil. But if the infiltration, if the rainfall is bigger than the infiltration capacity, which means the rainfall is more than the absorption capacity of the soil, it means that some of the rain will seep into the ground and some of the rain will be surface runoff. So because the rainfall is bigger than the capacity of soil absorption, so only some of the rain will be absorbed into the soil, and the amount of the rain which cannot be absorbed will be flowing in the surface or become surface runoff. And the factors affecting the infiltration will be, the first one is the height of the water layer above the ground level, which means we have here the ground level. This here we have like the ground layer. So the height of the water layer above the ground level means if we have here the water from the rainfall, the thickness of the water from the rainfall will be affecting the infiltration. And the second one is the type of the soil. The clay soil, sandy soil will be different regarding the infiltration capacity. And then the amount of soil moisture content that is already in the soil layer. So for the type of the soil which is wet, it means that the soil moisture is already have like big content inside the soil because it's already wet in the beginning. That's why the amount of the soil moisture content is affecting the infiltration, because if the amount of the soil moisture content is already high, it means that the infiltration cannot be as high as the dry soil. And here we have the fourth one is the state of the surface and soil cover, which means if the surface of the ground is, maybe the coverage of the surface is paving block or asphalt, it will be different, the infiltration. So if the soil cover has, for example, plants or grass, or if there is plants, there will be roots on the, like inside the ground before the groundwater level. So it will be affecting the infiltration also, because as you know, if we have like soil covered with the paving block, will be different with the soil covered with asphalt. It will also be different with the soil which is uncovered. So the infiltration will be different, because if the soil is uncovered, it will be easier for water to be absorbed in the soil. But if the soil is covered by, for example, asphalt, it will be more difficult than if the soil is covered by paving block. So the asphalt will be more difficult than the paving block for the infiltration, and the uncovered soil will be the most easiest for water to infiltrate into the soil. And then the last one is the soil mass transmissibility, is the ability of the mass of the soil to be transported, like how the soil can move the water within like with fast or slow speed. It depends on this soil mass transmissibility. It also depends on the type of the soil, because this transmissibility has like numbers, and usually the soil that have like big pores, which has big pores, it will have like bigger transmissibility than soil which has like small pores such as sand or clay soil. It will be has less transmissibility than the soil which has very big pores. And after infiltration, like some of the water infiltrates, and if the water stops in the soil moisture, and then it makes the soil moisture full, the moisture content is already full. So some of the water can also be transported into the groundwater level, which is called percolation. So the percolation is the process of flowing water by gravity from moisture content, MC here, to the layers below it. So here we have the soil surface, the blue line. Here we have the rainfall. Going into the soil surface, becoming the infiltration capacity here, FP. And after that, the soil which is contain the water from the rainfall, from the precipitation, makes the soil moisture, or here we have moisture content. And then after that, by gravity force, the water from the moisture content can be flowed to the layers below it, with the destination of the groundwater level. So this process affects the balance of the MC, which will later affect the amount of the initial infiltration capacity. So here, if we have the infiltration capacity bigger than the percolation in time interval of T, it means that the initial infiltration is less than the infiltration capacity. Initial infiltration capacity is less than the infiltration capacity here. But if we have the infiltration capacity less than the percolation, so the percolation is bigger, it means that the initial infiltration capacity is bigger than the infiltration capacity. So this percolation here, it is closely related to the initial infiltration capacity, the FO. Besides the water flowing inside the ground, we can also calculate it, how much water or how much the rate of the infiltration of this ground. For example, here we have a machine, a device, a measurement device called infiltrometer, which is used to calculate the infiltration capacity of the soil. So in a watershed, the infiltration capacity varies due to the season. For example, if it is a dry season, of course the water will be dry, and then because of the dryness of the water, the infiltration capacity will be higher because there is no water in the soil. So it also can be changed or can be varied because of the soil cover. For example, if the soil is covered by the grass, it will infiltrate water easily than the soil which is covered by the asphalt, for example. And the measurement of the infiltration rate, it can be used. The infiltrometer can be used to measure the infiltration rate, which consists of infiltrometer single ring or double rings. in this picture, it is the double ring. So as you can see from the above here, the picture, it is called double rings because it has like two circles here. And if you see through the soil, and you can see that some part of the rings is planted into the soil. And then here we have like the measuring device here, and so that we can measure the infiltration capacity of this particular soil. For example, here we have like the time of 4 times 10 minutes, and then we can measure the height of the water infiltrates. Here we have the first one is 6 millimeters, and then 5 millimeters, 4.5, 4.0. As you can see, it's decreasing because of the in the beginning the water can infiltrate easily because for example here maybe the soil is still dry, and then after that it's decreasing because from here they already have the 6 millimeters from the previous time step, so that it will be decreasing. And then after that, we can calculate the infiltration capacity, which is with units of millimeter per hour. So here we have 36 millimeter per hour, because here we got the 6 millimeter in 10 minutes, etc. This is the example of the top view and side view, and the example of the size, the unit size. Here we have 30 centimeters of the inner ring, and then 60 centimeters of the outer ring. So the diameter of each ring is different. And here we have the water level measuring instruments, the number 2. Yeah, this is called the double ring infiltrometer. For the single ring, it's the same, but there's no outer ring or inner ring. So the ring is only one. So there will be only one ring and the water level measuring instrument. We can also calculate using equations. The name of the equation is the Horton equation, because the person which found this equation named Horton. This Horton equation for determining the infiltration capacity is written here, like for the infiltration capacity after T duration of units of hour equals to the constant infiltration capacity, here the FC, constant one. So it doesn't depend on the time constraint, and then plus FO, the infiltration capacity at time equal to 0, like the initial infiltration capacity, the FO, minus FC. Here we have the constant infiltration capacity, and then times E, constant value of E, with the power of minus K. This is the constant for the soil and the surface, so it depends on the type of soil, K, and times T, the rainfall duration. Actually, this equation is used to calculate the infiltration capacity, which is in curve, namely DFP. So it it's calculating the FP by using the equation for each. Here we have two graphs here. For example, here this equation can only be applied if the rainfall is bigger than the infiltration capacity. So if the I is bigger than FP, we can use this type of equation to calculate the infiltration capacity, the FP. So here we have if I is bigger than FP. If the rainfall is bigger than FP, of course, some of the rainfall will be absorbed into the soil, and some of the rainfall will be going above the soil into the surface runoff. And how about if the rainfall is less than the infiltration capacity? So all of the rainfall will be infiltrated here, and then the equation will be different. We will not be using this equation, but we have to change this equation. This is the steps of changing this equation, this Horton equation, modified Horton equation. If we have like the rainfall which is slower than the infiltration capacity. So the first one, here we have the equation of this this graph here. So the integral of f minus fc. Here we have the fc is the constant one, and the f is the infiltration which is happening. And then integral of f minus fc times dt. And then we calculate the f first using the Horton original equation, and then f equal fc plus blah 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 is the same with the previous equation, which is written here. And then we change it, like we move the fc to the left side. Then after that we can move this f minus fc into the integral part here, and then we do the integral thing with this equation here. And then after that integral this f minus fc dt, and then we have this results f minus fc per k. And then for this f minus fc per k equal to f, big F, the capital F, and then we move k to the f, and then we got this f minus fc equal to capital F times k. And here we got this like two time steps. For example, for T1 and T2, we got this because the integral is for T until infinity. So here we try to use it for T equal 1 and T equal 2. And then we got this equation right here, f minus fc becoming f1 minus fc and f2 minus fc. Same goes with the f1 here, the capital F1 and capital F2. And then after that, we got this F2 equal to F1 minus integral F minus FC dt. And if the rainfall is less than the infiltration capacity, the infiltration capacity become equal to the rainfall, because all of the rainfall is going inside the soil through infiltration. That's why here we change it to F equal to I. And then we change this equation from the F becoming the I. Here we got this F1 minus I minus FC times dt. And then we got this equation F2 minus FC. This is from the previous one here. We have F minus FC per K. And then because this one is F1, we change it here F1. This one is F2, we change it here with F2. And then we can elaborate this equation again using F2 minus FC equals to F1 minus FC. We moved K, so we multiply with the K here. And then after that, we got this equation F2 minus F1, F2 equal to F1 minus K times I minus FC times dt. So it becomes the new formula which will be used if the rainfall is less than the infiltration capacity. So for this formula, the infiltration will be equal to the rainfall, so that the equation will be different than the previous one. So here we have the FP1 and here we have the FP2. So how to calculate FP2 is by calculating the FP1 minus K times F min FC times dt. So it will be clearer if we use this in the example because it has number. Here in the formula, we only have like this equation. It will be not clear if we are not using it with number. So there will be example. There will be example in the last section of this presentation. And regarding this infiltration capacity curve, it is also related to infiltration index. So this infiltration index is the average rate of loss such that the volume of the rainfall in excess of that rate will be equal to direct runoff. So this is the rate of loss, which is signing the volume of the rainfall more than this index will be equal to the direct runoff. So this infiltration index is the average of the water which can be absorbed into the soil. So the amount bigger than this index will be equal to the direct runoff. So the assumption of this infiltration index is it is constant throughout the storm or the rainfall duration. Actually, in the reality, it's not like that because, as you know, the storm of the rain or the rainfall duration is changing within time steps. For example, if we have rain in 4 hours, the rain in the first hours will be not the same, will not have the same amount with the rain within the second hours or third hours. But here, for the infiltration index, it is assumed to be constant throughout the storm or rainfall duration. It is best suited to applications in long duration storm or catchment with high initial moisture content. So if we have like high initial moisture content, of course, the infiltration indexes will not be that big because the water infiltrates into the soil will not be much because it already has high initial moisture content. And there are two types of infiltration indexes. The first one is P index, and the second one is W index. We will talk about this index more, and it will also related to it will be related to the previous one, the infiltration capacity curve. So for this infiltration capacity curve, there is this thing, the FC thing, the constant FC thing. It will be similar with this infiltration indexes. For example, here we have the P index and W index. You can read this as P index, and this one is W index. For P index, it is the average value of the rain intensity minus the volume of rain, which is equivalent to the volume of the runoff. So the average value of rain intensity, this is the intensity, the I is the intensity of the rain. And here we have the P index. And then if the intensity of the rain minus the P index, it will be the volume runoff, which means if there is this infiltration, if there is this rainfall or precipitation, and the water that coming right into the soil is this P index. This is the water absorbs, and then the runoff will be the upper one. So the intensity bigger than P index will be the volume runoff. This volume of the rain is also known as effective rain, or RF, which is the amount of the rain that causes direct surface runoff. This is the volume runoff, which causes the direct surface runoff, which means this is the water flowing in the surface of the soil. It can also be calculated with this equation. So the effective rainfall equal to the flow volume here divided with the catchment area. And the volume of flow can be calculated from the area of the hydrograph curve. So the amount of this hatched area or shaded area here is the volume of the flow volume, or the volume of the runoff. For example, here we have the data from the hydrograph. I hope you still remember the hydrograph. So hydrograph is the graph connecting between the intensity of the rainfall with the time duration of the rainfall. So here we have like the rain intensity of 30 millimeter per hour. And then here we have the duration of the rainfall of 1 hour, here 60 minutes, 120 minutes, 180 minutes, and 240 minutes. And then here we have the catchment area of 100 kilometers square and the flow volume of 5 million meter cubes. And then we have to calculate the P index. How can we calculate the P index? From this data only. So here we already know the rainfall intensity, the 30, 50, 30, 55, 25, and 10 millimeter per hour. At first, the P index is not right here. So for this example, at first there's not this line here. We have to look for this line actually. And then we have to calculate how big is the P index so that we can draw this line. So we can calculate it using this equation. First, we have to we have to look for the effective rainfall. Here we have the effective rainfall of 50 millimeters from this flow volume divided by catchment area. So as I already shown before here, the effective rainfall is the flow volume divided with the catchment area. So we have the effective rainfall of 50 millimeters. And then this effective rainfall will be equal to the area which is shaded here. So here we already have the line, but we are not sure how big is this V index. So we have to calculate it. And then we already know the area which is shaded here. For this 30, 55, and 25 bar chart, and then we can calculate the V index using this equation. So here 50 millimeters equal to 30 minus the V index times the time duration 1 hour plus 55 minus V index here, because this area which is shaded is equal to the effective rainfall, so we can use this equation instead. And then plus 25 minus V index times the time duration. After that, we got the V index equal to 20 millimeters per hour. So we know that this line here is located in 20 millimeter per hour of rainfall intensity, which means the effective rainfall is above this line, which is becoming the surface runoff, and everything below this line will be going as the infiltration. And the amount of this V index, it depends on the heterograph model. So even though the amount of the rain is the same, if the distribution of the rain is different, it will produce different V index. For example, here we have the heterograph model right here. If the amount of the rainfall is the same, for example, it is also 50 millimeters, but the distribution of this intensity is different. So the V index will also be different, because it depends on the distribution of the rainfall intensity on each duration of the rainfall. For example, here in each 1 hour, in every 16 minutes, it is calculated as shown in the heterograph here. How about the W index? So the W index is the average infiltration capacity during the rain. The differences here is if the rain is not uniform, the amount of the W index will be different with this V index. But if the rain is uniform, which means the intensity of the rainfall is the same. For example, in uniform rain, this heterograph will not be like this, but it will be like a straight line. For example, at the first hour, it's 30 millimeter per hour. The second hour will also be 30, and then 30, 30 uniform until gone. So it will be the same, not fluctuating like this. But it doesn't happen in the reality. It's rarely happen, because usually the rain is after it reached the peak, it will be decreasing. So if the uniform rain does happen, the amount of W index will be equal to V index. And then we can calculate the W index with this equation with the total of the rainfall minus the effective of the rainfall divided by the time duration. For example, in this previous example, here we have the total of the rainfall of 30 plus 55 plus 25 plus 10. And then here we have like 120 millimeter, 120 millimeter. And then we have the effective rainfall of 50 millimeters and duration of the rainfall of 4 hours. From this data, we can calculate the W index by using this equation, and we got this W index of 17.5 millimeter per hour. So that's why it is different with this V index, because the rain is not uniform. It is different within the period of time. It will be also different if the rainfall is the same. For example, it's the same 30 in every hour, and then we have this V index of 20 right here. So the W index will also be 20. And besides the V index and W index, we have also flow coefficient. So for the flow coefficient, it is the ratio between the effective rain and the total rain. So the total rain is the rainfall that's already that's pouring from the sky, and the effective rainfall is the rainfall which is becoming the surface runoff. So the flow coefficient is the ratio between the effective rain and the total rain. So based on this equation, this flow coefficient will be less than 1, because the total rainfall, of course, will be bigger than the effective rainfall. And from the previous example, here we have like the total rainfall of, here we have 30, 55, 25, and 10 millimeters. And then we got this effective rainfall of 50. And from this data, we can calculate the alpha, or the flow coefficient, by dividing the effective rainfall with the total rainfall. So we got this 0.417 as the flow coefficient. So 41% of the rain is becoming the surface runoff, which is flowing above the soil, and the other part of the rain is going into the soil infiltrates. And we can also like knowing how much discharge and recharge we got from like one heatograph here. For example, here we got this heatograph, and we already calculate the P index, for example, and then we can know the discharge and the recharge of particular rain by using this heatograph with calculating the area of this curve. The amount of the rain that causes direct surface flow is the discharge, here the upper one, and the amount of the rain which is not flowing in the surface is called recharge. The meaning of the discharge and recharge is related to the water that we can see and cannot see. For example, for the discharge, it will be useful when we design the channel. For example, here we have like drainage channel. We have to calculate the discharge of the rainfall, because this amount of the discharge we need to like drainage it into the part of the water bodies, for example, into the river or into the sea. It depends. And then for the recharge, we will get additional groundwater content here because of this recharge is the amount of the water infiltrates into the soil, which is becoming the soil moisture or moisture content, or can be also adding our groundwater level. So the groundwater level can be increasing by the water recharging from the rainfall. And this and the limit of this recharge and discharge is known as this V index. So the line of this V index, it is related to amount of the water discharging and the amount of the water recharging into the soil. This is the example of this calculation of infiltration and percolation. So from this example, we can also use the equation that we already learned before, like the Horton equation. For example, here we have the data of the rain as shown on this hydrograph. As you can see here, the rainfall is happening in 200 minutes. In 200 minutes. So from the minutes of 75 until 150, there's no rain at all, and then it begins raining again during the minutes of 150 until 200. With the rain data as shown on this hydrograph below, and we got the field data here. We have the initial infiltration of 25 millimeter per hour, and then capacity of infiltration of 15 millimeter per hour. And then we have this constant of the soil. It depends on each type of the soil. Here we have the constant of 8.10 power of -3 per minutes. Here we have to calculate the the V index and W index. How can we calculate it? First, we have to draw the curve of the infiltration capacity on the rain hydrograph using this equation. So we have to draw the curve of the infiltration capacity, the FP curve, using this following equation by comparing the rainfall and the capacity of infiltration. So here we have the infiltration, the FP. The FP is already known as capacity of infiltration here, 25. So the initial is 25. For the initial infiltration of 25, we have to compare the rainfall, the intensity of the rainfall on each duration by using the infiltration capacity for each time step. For example, for the first time step, 0 until 45 minutes. Here we have the F45. We have to compare first with the F0 because the first one is 0, which is F0. Here we have 25 millimeter per hour. And then we have the rainfall intensity of 20 millimeter per hour. And then 20 is less than 25. Because 20 is less than 25, we have to use this equation. So the equation using this FP2 equals to FP1 minus K times F min FC times delta T. Delta T here, and then we use the number that we already knew from the data. For example, for the FP1 is 25 because it's the FP1 is time step 1 and time step 2. For here, we have time step 1 as 0, and then time step 2 as 45 minutes. So we use the F0. F0 is equal to 25 minus the K we already knew from the data, and then F minus FC. Here we have the F of 20, and FC is known from the data also is 15 times delta T. Here we have like 0 until 45 minutes. And then we calculate it using this equation. We got this infiltration capacity for 0 until 45 minutes. After that, we draw it 23.2 here. And then we calculate again for the next time step. Here we got 45 until 75 minutes. And for this 45 until 75 minutes, we have to compare whether the rainfall intensity and the capacity of the infiltration is bigger or smaller. And then we compare it using this here we have the rainfall intensity of 35, and then we compare it to our previous FP, which is 25. For 35 is bigger because 35 is bigger than 25. So we use this equation because I is bigger than FP. And then we can use this equation using this Horton equation right here, the original Horton equation. And then we put the numbers. Here we got this 15 FC from the data, and then F0 is the F from the previous one that we already calculated here, 23.2 minus FC we got from the data, and then times E number times minus K, power of minus K times delta T. And then we got this 21.45 millimeter per hour. Here we got 21.45. Then slowly we can draw the curve. After that, for 75 until 150, we have no rain. Of course, it will be the rainfall intensity less than infiltration capacity because the rainfall intensity is 0 because we don't have any rain. So we have to use this equation, and then we put in the number, and then we got this 30.45 millimeter per hour. And then after that, we compare again for the next time step. For the next time step, it will be 150 until 170 minutes. And then we compare it. It has 45 rainfall intensity. And because of this rainfall intensity is bigger than this FP, the FP is from the previous one, 30.45. So we have to use this equation right here. And then by using this equation, we got this 28.17 millimeters per hour. And then we can draw it. From here, actually, we have to calculate also for the time of 170 until 200. But from the graph, we already know that this line will not be crossing this graph because it's too low, so that we can leave it like that. We can end it in this time step 170, because if we continue it, this this curve of the infiltration capacity will not reach this curve, and it doesn't make any difference for our calculation of the surface runoff. From here, actually from this picture, we still doesn't know how much is this V index, because we haven't calculated it, but in the end we will calculate it. And by using this curve of the infiltration capacity, we can know the volume of the runoff by calculating the area of the shaded area here. By calculating the volume of the area, we got the volume of direct flow or volume runoff is equal to 11.58 millimeter. So the height is 11.58 millimeters. From this runoff or this volume runoff, we can calculate the V index by using this equation. 11.58 equals to, here we have 35 minus V index, and here we got this 45 minus V index. And then we can calculate it by using this equation, and then we can know the V index is equal to 25.2 millimeter per hour. And after we got this V index, we can calculate the W index also by using this rainfall effective rainfall. Here we have this 11.58. It should be 58, not 56. But first we have to calculate the total of the rainfall first, which means we have to calculate the total of this all of the rainfalls from 20, 35, 45, and 20. Here we have 20, 35, 45, and 20. And then we got this rainfall total, and we can calculate the W index by rainfall total minus rainfall effective divided by the time duration of the rain, which is 200 minutes, equal to 3.33 hour. And then we got this W index of 13.78 millimeter per hour. And then we can also calculate the flow coefficient by using the ratio of rainfall effective, here the volume runoff, the rainfall effective divided by the total of the rainfall, and it is equal to 0.2, which means the 20% of the rainfall is flowing above the surface, and 80% of it is infiltrates into the ground. Yeah, so that's all regarding the infiltration and percolation. Should you have any question, you can ask, because we still have a little bit of time here. I guess there will be an exercise regarding this, so that you can use this equation properly between these two. You have to compare first which one is bigger, the rainfall intensity or the capacity of infiltration. Yeah, I hope you are not like confused with the with these materials, because it's simply regarding the water which is going inside the soil and the water which is cannot go inside the soil, which has to be flowing above the ground, going into the drainage channel or other channel, with the destination of, like, for example, a river or sea, as you already know from our hydrological cycle. Obviously, the water which is going from the rainfall will be going back into the sea or into the river, and then evaporates again and then produce rainfall again. That's why we call it hydrological cycle. Okay. Do you have any question?
Excuse me, ma'am, I have question.
Yeah.
For the first example, to calculate the P index.
Yeah, P index. This one?
The next slide.
This one?
Next.
Or the previous one, I guess.
I think previous.
This one.
Okay, yeah, that
Yeah.
one. There is a times one for the calculation. I don't know where they're coming from. The one.
Okay.
Yeah.
One is equals to the duration, because it's in hour. Here we have 60 minutes, so we have to convert it to hour. And then, for example, for the first one, 0 until 60 minutes, which means 1 hour, we have 30 millimeter of rainfall. So here we have 30 minus P index times 1 hour. It's the same with the other value, because we calculated in every 60 minutes. Like, for example, here 0 until 60, and then 60 until 120, 120 until 180. So it is in every 1 hour. That's why it's times 1. It will be different if we calculate it in, for example, in 45 minutes or 30 minutes. It will be like 0.5 or 0.75. So we converted the minutes into the hour, because of the units of the P index is millimeter per hour. Is it clear?
Okay, clear, ma'am. Thank you.
Okay, you're welcome. Is there any question again? Yeah, I will share this presentation in the classroom. Okay. No more question? Oh, still recorded.